Hello guys, in this video we are going to discuss the solution of the problem sum of bit differences. So let us look at the problem statement. The problem statement says that given an array integer ARR containing n elements, find the sum of bit differences between all pairs of elements in the array, and the bit difference of a pair x, y is the count of difference bit at the same position in the binary representation of x and y. So for example, the bit difference for 2 and 7 is 2, and that is because the binary representation of 2 is 0, 1, 0, whereas the binary representation of 7 is 1, 1, 1. So if we see this, the first bit and the last bit differs. Okay, the first and last bit differs between the two numbers, because of which the bit difference for 2 and 7 is 2. So let us try to understand the problem statement with the help of an example. So here n is equals to 2, and these are the elements of the array which is given to us. If we see here, all possible pairs in the array is 1 1, 1 2, 2 1 and 2 2. Please note 1 2 and 2 1 are two separate pairs which is mentioned in the question. So for these, if you see, so 1 1 the bit difference is 0, there isn't any bit difference. Similarly for 2 2 the bit difference is 0. For 1 2 the bit difference is 2, and for 2 1 the bit difference is 2. And if we add all these numbers, we will get 4, and this 4 is what we are returning over here. So that's about the problem statement, folks. Now let us discuss the solution of this problem. So in order to understand the solution of this problem, let us take an example where n is equals to 3 and the elements of the array are. So let me just go ahead and represent all these elements, which is 1, 3 and 5, in its binary format. So this is the binary representation of 1, 3 and 5. So now let us compute the sum of bit differences of all pairs. And let me represent bit differences by BD. So first thing which we understand is the bit differences of pairs where the elements are equal. So the bit differences of 1, 1, the bit differences of 2, 2, and the bit differences of 5, 5. Okay, I'm sorry, this is 3, 3. All these bit differences are 0 because the elements are identical, and since the elements are identical, then there won't be any bit differences for them. Okay, similarly we also understand that the bit difference of 1, 3 is equals to the bit difference of 3, 1. Let us just list down all the pairs which we have. So similarly the bit difference of 1, 5 will be equals to the bit difference of 5, 1. And here the bit difference of 3, 5 will be equals to the bit difference of 5, 3. So these are the 9 pairs which we have. Now let us compute the bit differences of all these pairs. So we know that the bit difference of 1, 1, this portion we understand, and this will be equals to 0. Okay, now and since the bit differences of 1, 3 is equals to 3, 1, so we are going to compute the bit difference of 1, 3 also only. Similarly, we are going to compute the bit difference of 1, 5 and 3, 5. Okay, so now let us compute the bit differences for all these pairs. So let us compute the bit differences for the pair 1, 3. So if you look at our binary table or the binary representation of the numbers, 1, 3 differs at how many position? Well, at 0th position and at 2nd position, the numbers are same or the digits are same. Whereas at this position, the numbers differs here. It is on the first bit and the amount of time it differs is just 1. So the bit difference for 1, 3 will be 1, and this it differs on first bit. Now let us compute the bit difference for 1, 5. So for 1, 5, as we can see, it differs on second bit. So here is where it differs, second bit, and it differs for. Okay, so it only differs for second bit. The remaining bits are same. So let us go ahead and write it down. So it differs for 1 times, and the position where it differs is second bit. Now let us compute the bit differences for 3 and 5. So 3 and 5 differs at how many position? Well, 3 and 5 differs at second position, and on first position. So these are the two positions where it differs. So the bit difference is 2, and where all it differs? Well, it differs on second bit and first bit. Okay. So now if I want to compute the bit differences of all the pairs, then the bit differences of all the pairs is basically the summation of these 1 plus 1 plus 2 and twice of this number, right? The reason we are doing twice is because we know that the bit difference of 1 comma 3 is equals to 3 comma 1. So in order to accommodate 3 comma 1, 5 comma 1 and 5 comma 3, we are just multiplying this number by 2. So in this way, the bit difference will be 4 into 2, which is equals to 8. Okay. All right. So this is one way of solving it, which is basically you list down all the possible distinct pairs, you compute the bit differences between these pairs, and you do a summation of it, and we take twice of that number. Okay, or we multiply that number by 2 and we will get the bit differences. The other way of looking the same problem is, rather than computing or rather than operating on all pairs, what we are going to do is we are going to check the bits at which the elements or the pairs differs. So for instance, these are the distinct pairs which we have, right? And this pair 1 comma 3 differs on first bit. Okay, 1 comma 5 differs on second bit, 3 comma 5 differs on second bit and first bit. Okay, so the sum of all pairs will also be equals to how many times 0th bit differs plus how many times first bit differs plus how many times second bit differs. So if we add the values of all these bit differences, then also we will get the same output. So let us try to do that. How many times 0th bit differs? Well, 0th bit is not here, so it does not differ, because of which it is equals to 0. How many times does the first bit differs? Well, first bit differs for 1 and 2 times over here. So this is equals to 2. And how many times the second bit differs? Well, second bit also differs for 2 times, which is equals to 2. So here what will happen is this becomes equals to 2 plus 2, which is equals to 4. And remember, we have to do twice of this number. So this is equals to multiply by 2, which is equals to 8. Okay. So an optimal way of solving this problem relies on computing how many times a particular bit differs, okay, rather than operating on all pairs or all possible pairs, because if we have to operate on all possible pairs, then the amount of time we are going to take is n squared, whereas if we want to operate on bits, this can be done in order of n time. Okay, so in order to understand this concept more clearly, let us take one more example and try to understand this concept more clearly. So in this case, let us say the number of elements which is given in an array is 10, and the array consists of elements such as 1, 2, 3. So these are the elements of the array, and in this array I need to find the sum of bit differences. Okay, this is what we want to compute. So rather than operating on all possible pairs, we are going to check how many times does a particular bit differs. Okay, so in order to understand how many times a particular bit differs, what we are going to do is we are going to represent all these numbers in its binary format. So let us do that. So this is the binary representation of all the elements of the array, and in order to compute the bit differences, what we are going to do is we are going to compute how many times does the 0th bit was set to 1. Okay, so let us see this. How many times, so this is the binary representation. Now let us see how many times 0th bit was set to 1. Well, it was set to 1 for how many times? 1, 2, 3, 4 and 5. So here 0th bit was set to 1 for 5 times. Okay, similarly the first bit, how many times the first bit was set to 1? Well, 1, 2, 3, 4 and 5. How many times the second bit was set to 1? Well, it was set to 1 for 4 times. And how many times the third bit was set to 1? Well, it was set to 3 times. Okay, now we know that the sum of bit differences is also equals to the number of times 0th bit differs plus number of times first bit differs. And since here we are operating on 3 bits, so number of times second bit differs plus number of times third bit differs. Okay, so now let us compute each of these values. How many times the 0th bit differs? Okay, with this information, let us compute how many times the 0th bit differs. Well, the number of times 0th bit differs, so we know that the number of times 0th bit was set to 1 is 5. Okay, so let me just write it down like this: set to 1. So number of times 0th bit was set to 1 is 5 times. So because of which the number of times it was set to 0 is equals to n minus 5. So in this case, which is equals to 10 minus 5, which is equals to 5. Okay, let us, just for understanding sake, let us list down the places where it was set to 1, or for the elements for which this bit was set to 1. Okay, so for the elements for which the bit was set to 1 is 1, 3, 5, 7 and 9. Okay, so for these elements the 0th bit was set to 1. Okay, so these are the 5 elements, and for the number of times it was set to 0 are for these elements, right? The remainder elements, which is 2, 4, 6, 8 and 10. So these are the 5 elements. Now all pairs which will be formed with this, right? So I'm talking about pairs such as 1, 3, 1, 5, 3, 5, and similarly n number of pairs. All the pairs which will be formed here, the bit difference, the 0th bit, since the 0th bit remains 0, sorry, the 0th bit remains 1 for all the cases. So the bit difference for 0th is bit is 0, right? The bit difference is 0. Similarly, for all the pairs which we will be getting over here, which is 2, 4, 2, 6, 6, 8 and so on, the 0th bit, the bit difference for 0th bit is again 0 here for all the pairs which is formed internal to this set. Similarly, all the pairs which are formed internal to this will be 0, but all the pairs which will be formed by the cross multiplication of these two set, right? So I'm talking about the pairs such as 1, 2, 1, 4, 3, 4 and so on. So all the pairs, so in the Cartesian product, right? So one way to understand is 1, 3, 5, 7, 9 is one pair, is one set, and the Cartesian product we are doing it with 2, 4, 6, 8 and 10. So all the pairs which will be generated here, the 0th bit will differ, right? Because in this set the 0th bit is set to 0, and in this set the 0th bit is set to 1, because of which the 0th bit will differ for one time, right? So how many such pairs are there? Well, the number of pairs is equals to 5 into 5, right? So 5 elements from here and 5 elements from here. So the numbers of pair is equals to 25. Okay, so now let us formalize this. So we know that the number of times the 0th bit was set to 1 is 5 times. Okay, so number of times 0th bit is set to 1 is 5 times. So we know that the number of times 0th bit is set to 0 is n minus 5. In this case, this is equals to 5. So the total number of pairs where the 0th bit differs is equals to the cross product of this. So 5 into 5, which is equals to 25. Similarly, if we want to compute the number of times first bit differs, right? So if we want to compute the number of times first bit differs, this is again equals to 5 is the number of times first bit was set to 1, then the 5 will be the number of times the first bit was set to 0. So this is again equals to 5 into 5, which is equals to 25. Similarly, the number of times second bit differs, this will be equals to how much? So the number of times second bit was set to 1 is equals to 4. So this is equals to 4 into 10 minus 4, which is equals to 4 into 6, which is equals to 24. Similarly, the number of times third bit differs is equals to, so number of times it was set to 1 is 3, right? This value. So 3. So this will be equals to 3 into 10 minus 3, which is equals to 3 into 7, which is equals to 21. So our answer will be equals to 25 plus 25 plus 24 plus 21, and remember we have to multiply this entire unit by 2. So this is our answer. So that's the approach, folks, or that's the discussion of the solution. Now let us see how we will be able to code this. So the code looks something like this. So what I am doing is that I'm maintaining an array which is bit count, which is basically how many times does a particular bit was set to 1. Okay. So bit count of 0 simply means that how many times the 0th bit was set to 1. Similarly, bit count I simply means how many times does the ith bit was set to 1. Okay, so that information is there in the bit count array with us, and here the the upper limit is 17, and this is coming from the quotient constraint, because here the element could be at most 10 to the power 5. So if you take a log base 2 of 10 to the power 5, we will get 17. That is why we are iterating, or the amount of space here we need is 17. Okay, now let's see how we will be able to do it. So I'm iterating on all the elements of the array, and this is the element. Using this logic, we will be able to find out at how many places or at what position the particular bit is set to 1. Okay, and accordingly we are going ahead and putting that information in the bit count. All right, so once we have the bit count with us for all the elements, what we are going to do is, for each of the bits we are going to check how many times it was set to 1 and how many times it was set to 0, and we are doing a multiplication of these two numbers, and that is something which we are storing into our answer, and towards the end we are returning twice of our answer. So that's about the code, folks. Now let us submit our solution. So our solution got accepted. That is all from this video, folks. In case if you have any question or comment regarding this video, please feel free to use the comment section and I will try to address them. Thank you.